Alright guys, so we're on to the next lesson. This is section 2.7 in the book, but it's a 1.4 lesson, so we're still in unit 1. We're talking about free fall now, so you probably have an idea of what free fall is, so let's start by kind of watching a video and trying to understand what's going on. So I have it set up as an Edpuzzle, so let me try to pull this up and move this, sorry, get it. So in this scenario, we are looking at, I'm trying to make this a bit better, sorry. We're looking at a person holding a book and a piece of paper. If you want to try this on your own, you can. So if you have a book handy, a piece of paper handy, you're just going to drop them from the same height. And we're going to think about which one is going to hit the ground first. So take a second and answer which one you think is going to hit the ground first. And we're going to keep going. And we're going to actually do the performance experiment. And we saw that the book hit the ground first. And I want you to think about why. So why would that happen? So throughout the years, many students come up with various explanations to why this happens. So they talk about the mass of the two objects, so the mass of the book compared to the mass of a single sheet of paper. They also talk about the weight of the book compared to the weight of the object. And those ideas generally are stated like the weight or mass of the book is more than the weight or mass of the paper, so therefore it falls faster. That's sort of the idea that people come up with. And that is not really a great explanation of why it actually does what you see, what happens. So so we have to come up with a better explanation. So the next experiment, I think, helps kind of give us more insight into the next one. Okay, so we're gonna drop the book on the piece of paper, and then we're going to scrunch them together and drop them there. So, so this is the question: what's going to happen if we scrunch the piece of paper up into a ball, and then we drop the ball of paper and the book from the same height? So, what do you expect to happen then? So, go ahead and answer that question.
So you have your classrooms, you shadow online, and you start
So which do you think is going to hit the ground first? Do you think it's going to be the book, the paper, or do they hit at the same time? And they hit at the same time. So what was different about the piece of paper when it was crumpled up into a ball versus when it was flat? The ball has less air resistance acting on it, so the influence of the air was not as great on the ball as it was when it was a piece of paper that was just a normal unscrunched up crumpled piece of paper. So so this is where we get into some of the ideas that we need to worry about. So this again. Okay. So so this concept of air resistance is important, and we want to try to ignore it in free fall situations. So here we go. So a free fall situation is one in which the object is moving only under the influence of the force of gravity. So the force of gravity is the only force acting on the object. No other forces can result in the motion, so there is no air resistance, there is no other object like force pushing or pulling on the object except for the force of gravity. Regardless of their masses, each object had the same acceleration, so they accelerated the same, they reached the ground at the same time. And on Earth, we commonly refer to this acceleration due to gravity as lowercase g, and it is negative 9.8 meters per second squared. The negative indicates that it is going downward. All right, so just to kind of test your understanding of free fall, I have a couple more questions. So we have, I think this is Ariana Grande, is going to drop a microphone, and we want to figure out when free fall starts and ends. So let me let you think about that. And free fall, so right now the mic is in her hand, so that is not free fall because her hand is applying a force to the mic, so that's not free fall. When would the mic be in free fall? When she lets go of it. So as soon as her hand is no longer touching the microphone, that is free fall. And that free fall is going to continue all the way until it interacts with something like the ground, so when it hits the ground, the free fall stops. So again, because there's a force acting on it. All right? let's talk about free fall here. So this person is going to throw a ball upward, and we want to know when free fall starts and when free fall ends. So think about this: the ball is in their hand. Is that free fall? No, because the force of the hand is applying the force. Then it's not only under the force of gravity. So as soon as it leaves his hand, is that free fall? And the answer is yes. We're going to ignore air resistance in all these cases because that's what we do to simplify the problems. You would need calculus if you wanted to include air resistance in problems. But as soon as this ball leaves his hand, that is considered free fall. So it might be moving upward, like the arrow would be kind of directed in the upward direction. Let me change color so you can see it. So this ball is going to move up. And as it moves up, you would imagine that it's going to slow down. It's going to reach some highest point, and then it's going to come back down. All of this is free fall until it interacts with something. So if he catches it at the same height, or if it falls all the way to the ground, that is all still considered free fall. The last one here, I forgot to update the example. This should be not throwing a ball upward, but maybe throwing it downward. So if we just change that down, so like dribbling a basketball, that kind of idea. So this is Allen Iverson, and that's Michael Jordan. Michael Jordan's about to get crossed up. It's a pretty famous play. So anyway, if you push the ball down, again, free fall starts after it leaves your hand. So if you're pushing down on it, that is not free fall. As soon as it leaves your hand, it's in free fall, and it is in free fall all the way until it interacts or another force acts on it. So that would be until it hit the ground. And then when it bounced up, that's another free fall situation, but we're not going to get into that. Okay, so let's track kind of a free fall scenario. This is like the example where the person was throwing the ball in the air, and let's kind of imagine what's happening and try to kind of give it some numbers that go along with it. Okay, so we're going to look at this ball, and it's moving upward at 30 meters per second. So positive 30 is the initial velocity, the starting velocity, and we're going to kind of try to track every second that goes by. So 1 second in the motion, 2 seconds, 3 seconds, 4 seconds, 5 seconds. So we're going to make this a little bit easier to do in our heads. So we're going to say that gravity, which is typically, if we're using it in a calculation, in a problem, it would be 9.8. But we're going to say it's approximately negative 10, because negative 10 and negative 9.8 aren't that different. All right. So I'm just going to make a chart up here. We've done this before, where we track velocity as a function of time. And time's going to be measured in seconds. And velocity is going to be measured in meters per second. So we're going to look at how the velocity is changing for each second of time. So at time equal to 0, our velocity is a positive 30. And we're going to add our acceleration to get to our next velocity. So our acceleration is negative 10 meters per second for each second that goes by. So that's our acceleration. So we're going to add a negative 10 to 30. So if I take 30, add negative 10 to it, I'm going to get a positive 20. So after 1 second of time, this ball is here at 1 second at this point, and it's moving up, and the velocity has gotten less. So that's our velocity at 1 second. If we keep tracking this at 2 seconds, we've had another 1 second time interval, so we'll have another change in velocity by 10, negative 10. So 20 plus negative 10 gets you a positive 10. So this might be at 2 seconds. And the arrow's gotten smaller. If we keep going 3 seconds, it's going to be going 0. So this is an important point here. So I'm going to draw the ball. We'll say this is the 3 second time interval. And if you're at 0 meters per second, what does that mean? It means you're stopped. So I call this position the highest point. And the highest point I refer to as the apex. That's the word that I use to make it sound important. And it is an important point because we solve a lot of problems with using information about the apex. And the information is that it's going 0 meters per second. So it's actually stopped at that point. Now, does it stay stopped? Does it get up there and just get stuck in the air? No, it's going to fall back down. So that's the point at which it changes direction. So it's going with a positive velocity on the way up because it's going directed upward, so up is positive. And then it gets to 0 velocity when it reaches the apex. If you look at these velocity vectors and you look at these velocity values, the velocity decreases as it goes up, and that's because there's a negative acceleration. So g is the acceleration, so the acceleration is negative in value, and it's equal to that, what we're approximating is negative 10 meters per second per second. So it slows on the way up because the velocity is positive and the acceleration is negative, so they disagree. On the way back down, I'm going to change colors on my arrow so we can kind of look at moving back downward. So moving back downward, after from 3 to 4 seconds, it's another time interval change. 0 minus 10 would be a negative 10. That's a really big negative sign, sorry. So negative 10, so it's moving down at negative 10, and then, so that's at 4 seconds of time. At 5 seconds, we'd add another negative 10 to it, so negative 10 minus 10 is negative 20 meters per second, so it's got a bigger arrow in this section from 4 to 5 seconds. And then finally, the last section, when it returns to hit the ground, add another negative 10 to this, negative 30. And that would be at 6 seconds. So let's look at this scenario a little bit and look at what's happening. So again, we said that it was slowing down as it rose. So as it moves upward, it slows down. What's happening on the descent as it falls? As it falls, it's going to speed up, and that's what's happening. People think that it's not speeding up because of the negative values, but the number's getting bigger. Remember, the negative just indicates downward. So don't get confused by that. The reason why it's speeding up on the way down, we have a negative velocity, and our acceleration is also negative because the acceleration in the y direction is always this gravity constant. So it is always negative 9.8 or negative 10. So they agree. Agreement means speeding up. So that is speeding up. So gravity is pushing it or pulling it the same way that it's moving. In that case, on the way up, it's pulling the opposite way that it's moving. So that's why it slows down. So that's really important. Another fact that I want you to notice is if you check these times out, or the times and the velocities, like whatever position it's at in this motion, so if it's at the same location, it should have the same velocity. It's just one's directed upward, one's directed downward. So if you look at 1 second and 5 seconds, they're both going 20 meters per second. One's positive, one's negative. If we're looking at 2 and 4 seconds, it'd be positive 10 and negative 10. If we're looking at 0 seconds and 6 seconds, that's 30 and negative 30. Remember, we don't worry about after 7 seconds because that's when it's no longer a free fall. So this modeling and way that we explain it doesn't work after it bounces and hits something and then eventually stops. All right. So when an object reaches the highest point, the apex, its velocity is 0 meters per second because it's stopped. It has to change direction from going upward to come back down. When it reaches its highest point, what is its acceleration? The acceleration in free fall, that's supposed to be an A, is always equal to g. So it's always negative 9.8. There will be questions about this throughout this presentation and other presentations. People think that the acceleration changes. It does not. It is a constant acceleration of negative 9.8, or we approximate it to negative 10. And then when an object starts and returns to the same level, compare the initial and final velocities. We say there were equal. And we compared the time up and time down. I didn't do that, but let's go back. How long did it take to go up? It took 3 seconds total. So it went from 0 seconds to up to 3 seconds. And then to come down, it went from 3 seconds to 6 seconds. So that's another 3 seconds. So if we're returning to the same level, and this is an important fact as well, you'll use it. So when it returns to the same level, the time up is equal to the time down. So I'll draw an arrow for up and an arrow for down. So if it returns to the same level. Now, if it's not returning to the same level, like if we do something like this where we throw something up and it goes and lands on something and stops, this time up to the apex is not equal to the time down. Or if we were standing on a cliff and we threw something up into the air and it fell and went further down, that isn't going to be the same time either. But if it's returning to the same level, their speeds are the same, the time up and the time down is also the same. All right, so let's check a couple questions. So here you go. An arrow is launched vertically upward here. It moves straight up to a maximum height, c, so that's the what? That's the apex. And then the trajectory is noted, so it shows you this goes up and comes down. At which point of the trajectory is the arrow's acceleration the greatest? That's the first question. The least. Again, we're ignoring air resistance and only the force of gravity is acting. So this is one of those tricky questions that I said was going to come up later. The acceleration is equal to g at all points. So it's always that negative 9.8 meters per second squared. So this is, they are all the same, is the correct answer. Okay. Some other ideas with free fall. So we talked about how to solve kinematics equations last time, like one-dimensional horizontal. Free fall is really the same thing. It's just you're rotating it 90 degrees and sending it up and down. There's a constant acceleration of gravity. So all the equations that we discussed previously, they all apply to this. All we had to do is substitute in g for a and delta y for delta x. So these equations we had on the previous lesson with x's here and a's, but it's really the same techniques in solving and everything. So we're going to jump in and solve some of these problems. We got a couple to get through. So in this first one, it says a construction worker drops a brick. So I'm going to draw a brick from the top of a building. I'm going to write the word drop because that's important. This is supposedly an accident. He drops it. It's not like throwing it upward or throwing it downward. So the word drop implies an idea that we're going to come up with in a second. We want to know what's the velocity of the brick after it's fallen for 4 seconds, and we want to know how far it has fallen. So velocity and how far, those are the questions. So as it drops, it's going to pick up speed. So there you go, that's a good enough picture. It doesn't have to be complicated. And then I'm going to set up the table. In our table, we have the same variables, except instead of x, you have y. We still have initial velocities and final velocities. Instead of having acceleration, we have the acceleration due to gravity, and we're on Earth, so we know that value. And then we have our change in time. So first thing I'm always going to be able to plug in, as long as we're on Earth, and most of our problems are going to be dealing with Earth, we get 9.8 meters per second squared. Let me change this font to make it a little easier to write. Thickness of the pen, that's not it. 4 seconds is our time period, so we're going to write a 4 in the time. And you might say there's only 2 numbers, so like we know gravity because that's always constant. They gave us the time. We need 3 out of the 5, is what I explained in the last video. So sometimes it seems like they don't tell you enough information, but it's implied, or you just use context clues to figure it out. So this word drop I mentioned was important. When you drop something, the initial velocity is 0. Another way to come up with this and know that you need to figure out the initial velocity, or you need to know something about the initial velocity before you can solve it. This asks for what's the velocity of the brick after it's fallen for 4 seconds. So for part A, we're solving for the final velocity, so I can put a question mark there. In part B, it asks for how far is the displacement. So for part B, that's going to be the question mark. So if you're going to solve for those later, they're not going to give it to you in the problem. So this is the idea. So it's because it's dropped, and we dropped the object, the initial velocity is 0. So I'm going to go back to these equations. I'm going to pick the equation that makes the most sense for this first part A. So part A, we don't have the change in y. That's the thing that's not given. So I want the equation that doesn't have that. So if I come back here and take a screenshot of it, it is the first one. So the first equation there is what we're going to use. And again, I'm just going to type to make it a little easier. So we're looking for VF. VI was 0 because it was dropped. Gravity is negative 9.8. And the time was 4 seconds. So this one isn't very complicated. You just multiply negative 9.8 times 4, and you'll get the final velocity is equal to negative 39.2 meters per second. Now, just to clarify and make sure I point this out, the negative here means that the object is moving down. So that is what you want. the object's moving down, you need a negative velocity. If you got a positive answer here, that wouldn't make any sense because somehow you dropped it and it started going upward. So that's part A. Part B wants to know how far it's dropped, so we can put in negative 39.2 here and then use whatever equation we want to solve for delta y. So again, for part B, I suggest you to pick one that's already set up to solve for delta y, so either the second equation or the fourth equation. The fourth one, again, always looks easier to me, so I'm going to plug in there and use it. So if I move that over here and then start typing in my ideas. So I need a delta, get that set up. So delta y equals 1/2. The initial velocity was 0. Final velocity was negative 39.2. It's important you put in the negative here, otherwise you're not going to get the right solution. And then time is 4 seconds. So we're going to go ahead and do that math in the calculator. And, always use your calculator, that's fine. So half of 4 is 2. 2 times negative 39.2 is going to give me a negative 78.4 meters. Negative, again, implying that it is down. Again, if you didn't put in the negative and you got a positive value here, this wouldn't make sense because somehow you dropped it and it moved up 78.4 meters. So hopefully this is just, again, it's pretty basic once you have the ideas down for the problem solving. It's just now we've turned it vertically instead of going horizontally. Next problem, tennis ball is turned straight upward at a speed of 22.5, so it's got initial velocity going up. As it rises, it's going to slow down, so I have some arrows getting smaller. We'll just say it reaches the highest point. At this point, that's the tennis ball. It's somehow turned blue, and then it's going to come back down, and it describes that you catch the ball at the same height that you threw it. We want to know how high above the release point does the ball go, how long is the ball in the air, and then at what velocity, magnitude, and direction, so that sounds hard, but it's not that bad, is the ball traveling when it's caught. All right. So again, setting up the table. Same 5 variables, change in position in the y direction, or displacement in the y, initial velocity, final velocity, gravity, and time, acceleration due to gravity and time. So initial speed, 22.5, that seems pretty obvious. That's positive 22.5 meters per second. Gravity is negative 9.8, so I can always fill that in. That could be the first box if you wanted to do that all the time, meters per second squared. And then, again, it seems like we don't really have everything. The first question, part A, wants to know how high above the release point, so I'm going to write out a question mark here for A. And how high would be like the maximum height, so that's the apex. So again, if you get apex, that's an important idea. So the apex height would be delta y. That means our final velocity or apex velocity at the apex is also 0. So we use that rule, that idea quite a bit. So now we have 3 things. We're looking for delta y. We want the one without time. Going back to the slide, figuring out which one of these equations doesn't have time, no time, so it's got to be that one. So copy that. Coming back to here. And we're going to plug in the values. So it's just doing algebra. After you've done the part up here, it's just really algebra. It's not overly complicated math. It's just kind of doing the work. So final velocity is 0. We're going to try to square that, and that's still just going to stay 0. 22.5 is going to get squared. Plus 2, negative 9.8. Make sure you make it negative. If you don't, you will mess up your problem. And then we're looking for delta y. So let me get the delta and then y. So going through it, 0 squared is 0. 22.5 squared is 506.25. This is going to be negative 19.8. And then we have our delta y again. All right, so just a point of contention here. Sometimes people try to solve this incorrectly, and the most common math mistake I see is they take the 506.25 and they try to add it to the negative 19.8. These two ideas, so the two ideas here, they are combined through multiplication. So that is one kind of term, and you can't just like add the coefficient of a term to a number and get an answer. That's not how it works. Let's see if that, no, let me just make this bigger, I guess. There we go. So we can't do that. So what we have to do mathematically, just to make sure we're all on the same page, we're going to take either of these terms over. I'm a positive person, so I try to make things more positive, get rid of negative signs, so it's easier for me. So I'm going to make the 19.8 on this side positive, because it goes to the other side, delta y equals 506.25. And then we divide through by 19.8 on both sides. So that drops out. For your answer for delta y, you should get something like 25.83. It's a positive number. That's going to be in meters, so that seems pretty good. So that was part A. Part B wants to know how long is it in the air. So I'm going to do this on another slide because I've run out of room already. So the time in the air, again for our chart, and let me copy the ideas that I have. For our chart here, we have the initial velocity, final velocity, gravity. So we can solve for time, but this is going to get us our apex time, or the time going up. So that is not the total time. And if we think back to our idea, it's going up and coming and returning back down to the same time. So if we take our total time, which would be the time it takes to go up and the time it takes to come back and fall down to the same height, we're going to take this number and we're going to double it. So the time up plus the time down will get you the total time. You could write it as a subscript too, that's fine. So I want the equation that doesn't have delta y. Coming back over here, this is the equation that doesn't have delta y, so let me snatch that. And I'm going to pull that over here, and we're going to go ahead and plug in and solve. So at the apex, the final velocity is 0. The initial velocity was that 22.5 plus a negative 9.8, and then the delta t. So I'm going to take the negative 9.8 delta t to the other side.
Good. How are you doing?
When I do that,
So, Brock asked for a haircut.
it's equal to 22.5. When you take it to the other side, it becomes positive, so that negative is no longer there. And then you divide through, and you should get something like
He said to do, now he works until 4 o'clock in Dover, or 3, maybe about 3:45.
Sorry, the mouse is not responding the right way.
We're talking.
So delta t, and this is the time just going up, is equal to 22.5 divided by 9.8.
You would check maybe Thursday or Friday before tomorrow, because I know tomorrow he wants to do something.
It should up. Which again is going to be equal to 2.3
so that's the
seconds.
He works all this week till.
So 2.3 seconds. We don't want the time up, we want the total. So if get the total, we're going to take that and multiply it by 2.
Inside the day also.
So the total time is equal to 4.6 seconds.
Let's put him down.
There we go.
And then tomorrow, I had said, don't look at tomorrow, but even tomorrow in the evening.
The last question we have here is just another one where you're doing the same thing. So I'm going to skip that one on this video and let you guys try to figure it out yourself. I will post the answers here so that you know what you should get. So for part A,
What about the following?
the initial velocity, you should get something like 49 meters per second.
Yeah.
And then for the, that's the initial velocity VI. How high did it go? You should get 122.5 meters in the air for delta Y, or change in Y. Okay, so those are the answers you should get. If you don't get those and you need help on that, just ask me next time you see me in class. All right, talk to you guys later. Be well.